Welcome to day 45, Supervised Learning. In today's session, we will dive into the concept of linear regression and logistic regression, two fundamental techniques in machine learning. We will also explore their real-world applications and walk through hands-on examples. Supervised learning is a type of machine learning where we train models on labeled data. This means that the input data comes with known output labels. The goal is for the model to learn from this data so it can predict outcomes on unseen data. A few common examples include predicting house prices or detecting spam emails. In supervised learning, we use the input features to predict an outcome. Linear regression is a technique used for predicting a continuous numerical outcome. For example, we could use it to predict house prices based on features like square footage, number of rooms, and location. This method assumes a linear relationship between the input features and the output. In other words, as the features change, the output changes at a constant rate. In linear regression, we define a model as a linear equation. The model predicts the output based on the input features. The cost function, known as the mean squared error, measures how far off the predictions are from the actual values. We use a method called gradient descent to minimize this error and find the best fitting line. Now let's look at a hands-on example. Suppose we are predicting house prices based on various features. We will start by pre-processing the data, training the linear regression model, and then visualizing the results. With tools like scikit-learn in Python, we can easily implement this and generate a plot showing how well our model fits the data. Now let's move on to logistic regression. Unlike linear regression, which is used for predicting continuous values, logistic regression is used for classification problems. It predicts the probability of an outcome belonging to a certain class, like predicting whether an email is spam or not. The key function used here is the sigmoid function, which converts the model's output into a probability between 0 and 1. Logistic regression works by calculating the log odds of a certain event and transforming it into a probability. The logistic function or sigmoid function output values between 0 and 1. The model's cost function is cross entropy loss, which measures how well the predicted probabilities match the actual class labels. In a practical example, let's say we are predicting whether a student passes or fails an exam based on study hours. By pre-processing the data and training a logistic regression model, we can classify the outcomes as either pass or fail. Evaluating the model's performance involves looking at accuracy, precision, recall, and other metrics to understand how well it is predicting these outcomes. When building models, we need to be cautious of overfitting and underfitting. Overfitting occurs when the model fits the training data too well, capturing noise and leading to poor generalization. Underfitting happens when the model is too simple to capture the underlying patterns. Regularization techniques like L1 and L2 regularization can help prevent overfitting by adding a penalty to large coefficients. Once we have built our model, we need to evaluate it. A common practice is to split the data into training and test sets to assess how well the model generalizes. We can also use k-fold cross-validation to validate the model's performance by splitting the data into multiple subsets and training the model on different combinations. This ensures that the model performs well across different subsets of the data. In machine learning, the performance of a model can often be improved by tuning hyperparameters. Hyperparameters are the settings that control the learning process, like the learning rate or regularization strength. Methods like grid search and random search allow us to systematically explore different hyperparameter combinations to find the best configuration for our model. Let's put everything together in an end-to-end project. We will load and clean the data, train a model using either linear or logistic regression, and evaluate the results. For example, in a project predicting heart disease, the model could classify patients as either at risk or not based on features like age, blood pressure, and cholesterol levels. To recap, we have learned that supervised learning involves training models on labeled data to predict outcomes. We have covered both linear regression for numerical predictions and logistic regressions for classification tasks. It's essential to practice these concepts through hands-on examples to fully understand how they work and how to apply them effectively. For homework, I recommend implementing linear and logistic regression on new datasets. You can experiment with regularization techniques like the ridge and lasso. I also encourage you to explore Kaggle competitions where you can apply these techniques to real-world problems and further sharpen your skills. Thank you for your time today. I hope you enjoyed this session on supervised learning. Don't hesitate to revisit any of the examples we covered and experiment with them on your own.